Okay, everyone. I just want to explain what's up here, what's due this week. Well, it was exam week, so there's nothing due until Thursday. And this homework 9 covers what we're doing today. It's chapters 16 and 17. And then you have, it looks like there's a whole lot due here. Well, there's the only one, remember, the only one that you have to do are the ones in red. So the only thing that's required is this R assignment that's due Friday at 11:59 p.m. Now, I strongly recommend you don't wait till after 5 on Friday. People have been doing that and then emailing me saying they can't get, there's some glitch. Please, we have office hours 2 to 5 all week, so try that ahead of time and you will get help on that R assignment if you need it. So now we have these, all the rest of this is bonus, and the survey I'll post is not posted yet, but I'll post it soon. And these pre-lectures are our usual ones. Now, what is this extra bonus pre-lectures on chapters 19 and 20? Those are chapters that we're not covering this semester. They're in your notebook, but we're not covering, so you're not responsible on any homework, exams, anything. But I think it would be useful to some people, so if you want to do them, you'll get extra bonus points on those. All right, now that's it for now, and let's just go to the document camera. All right, so what we're going to be doing today are 2 new significance tests. So far we've done the z-test and the t-test. Well, now we're going to be doing 2 tests involving the chi-square distribution. The first one is the Chisquared Goodness of Fit test. So when do we use those? Well, we use them when we have more than 2 categories. When we have 3 or more categories. Remember with 2 categories, like a 0-1 box, like if you wanted to see if a die was fair or not, wanted to see if it came up heads too often or something like that, you would just say coded as 0 and 1. And then we could we did a z-test, either for the sum or percent in each category, either way. But now, if you have more than 2 categories, like not just yes and no answers, but let's say it was yes, no, and unsure on a survey. Yes, no, and unsure. We wanted to count all 3 categories. Well, then we have a problem because how do we assess the differences? Remember, our statistic is usually the observed minus the expected, a difference. Well, if we have more than one difference, in 2 categories, you just have 1 difference. But if you have 3 or more categories, how do we combine those differences? Because the positives and the negatives will cancel out. So what do we do? So for example, suppose we wanted to test whether a 6-sided die is fair. And we have 6 differences to consider, okay? We can't just sum the 6 differences because some will be positive and some will be negative. So what do? We could take their absolute values, but that's not generally what we do in statistics. Instead, we square those differences and then sum them. And we get a statistics that involves the sum of squared differences. So the statistic we're going to be using is called the chi-squared statistic. And this is... So the key point is we're going to be having more than 2 categories. So if we had, for example, on our next page, we're going to do this example with the die. Is the die fair or not? And we're going to have 6 differences, and we can't just sum them because some will be positive and some will be negative. So what do? We square the differences. Okay, that's the key. And we get this statistic that looks like this. This is our chi-square statistic. And the numerator, it's the observed minus the expected, and we're squaring it. This denominator might look a little unexpected to you. Why isn't it just the standard error, our usual standard error? And then we could square it. Well, the chi-square statistic really is that. The chi-square statistic, we can come down here, and the chi-square distribution is the sum is actually just what you'd think. It's right here. It's the sum of independent z squared. So it's really is like, so chi-squared really is the sum. This is sum. It would be the observed minus the expected, observed minus the expected, over some standard error, not this frequency, some standard error. And then you'd square it. So this would be like your z-squares for each category you have. And it doesn't look like that only because in this particular test, the chi-squared distribution does look like that. In this particular test, we don't have independent z-squareds. We don't. They're not independent, and that's explained here. So I can say, why not just look like a z? Why not SE here and then square it? Why not that? SE squared in denominator. And it's because we're using a chi-square distribution, but just because in this example we're going to be using the categories aren't independent. They're going to have only one less degree of freedom. So we tweak it and explained here because the categories aren't independent. So this really does work out to be a chi-square distribution. And here's the explanation for it, sort of. Because the categories aren't independent. But the best way to look at this is to do the example, and then you'll understand what you won't understand it until I do the example. All right? So let's do the example. So we roll a die. We want to see if a die is fair or not. Okay, with a coin, when we wanted to do that, we could just do a z-test. But now, think about it. We want to see. So we have this. Our null is that the die is fair. And any differences we see, even though we rolled it 60 times, right? And look, it looks like we got out of the 60, you'd expect even numbers here. We got too few here and too many threes. But is that just due to chance or not? Okay, that's the idea. So let's just translate it into a null, into a box model. And the null, here's our null box. And as usual, in probability problems like this, games of chance, we make it for a single play or a single roll of the dice here. So the null box is for a single roll of a die. Okay? And what do we have? It could come up 1. I'll make these little tickets. 1. I'm making it like this because these are just categories. 1, 2. They're not really numbers. They could be colors. 1, in this case, for this example. 1, 2, 3. 4, 5, that's a 5, sorry, and 6. Okay, so there's just 6 tickets in here. 6 categories, right? So there's 6 tickets, right? And what are we going to do? We're going to draw randomly from here. First of all, our null. What's our null? Our null, H naught, is that the die is fair. That our observed data fits this model good. It's a goodness of fit test. Fits this novel well, fits this novel good. So the die is fair. And what you're thinking is that our observed data, this is what we did to test it, our observed data fits good, fits this model good. Because it's called the goodness of fit to help you remember it, right? That this is consistent with this model. And what's our H alternative is, the die is unfair. And this is very unlikely This does not fit this model. Observed data does not fit good. It doesn't fit that model. There's too many. It's too uneven. Okay, so we have to look at all the categories. So that's what I'm doing here. So now let's think about it. Here's what you observed, and that's given. So this is given to you. This is always the observed count. First of yeah, these are counts. They're always counts. And this is given to you. So the observed count, frequencies or counts, is given. Okay, and this is the expected count that depends on your model. So from our model here, we have 60 rolls, right? So how many we get for each has to sum up to 60. We happen to get 4 of these ones, 6 of these twos. But if the model was fair in the long run, what would you expect to get? Wouldn't you expect to get an even number of each of them? Wouldn't you? Wouldn't you expect to get 10 for each? Because each ticket is equally likely, right? So the expected is just, you'd expect 1, 6, 1, 6, 1, 6, 1, 6. 60 divided by 6, which is 10 for each category. All right, and now let's fill out this chart and see what we're doing with these chi-squares is we're saying, okay, how big a difference did we get? We didn't get exactly 10 like we expected. We got 4. So our observed minus our expected, we got below it by 6. 4 minus 10 is 6. We got negative 6 here. We got negative 4 here. Here we got 7 more than expected. Do you understand? So here we got 6 more than expected, 2 below, and 1 below. Now, what do you think, if we added these all up, what do you think it would have to be? What do you think? It always is going to be the same thing, and what do you think that is if you added these up? 0. It's always going to be 0. Because what we're doing is we're really taking the deviations from the average, really, from what the overall expected average. So, yep, we'd expect this to be 0 as usual. So always check that, because if it doesn't sum to 0, you did something wrong. All right, so now it sums to 0, so that's not a good measure of how big these are. We could take the absolute value, but we don't in statistics, except in unusual cases. So usually we square. Like usual, we square. So we're going to square every one of these differences, and that will remove the sign, so the positive and negatives don't cancel out. So we get 36, negative 4 squared is 16, 49, 6 squared is 36, 2 squared is 4, and 1. Okay? So that is a good measure of our differences, all right? And now what we're going to do is we can sum them here, and if you did, you'd get 142. But I want you to beware that if they have different expecteds, don't sum them here. So let's just say that. So right here, and you'll see why in a minute. Only sum them all here when expecteds are the same. Here they're all 10. Because really what our chi-square statistic is, if you recall, was, I'll write it down here because it was on the previous page. Our chi-square statistic that we're using is going to be the sum from the first category for all the categories, all 6 of them, of the observed minus the expected squared, the whole thing squared, over what we'd expect. And if this is different, we'd be summing fractions with different denominators. Okay? So here we'll do it separately. as if these denominators were different, because that's, if they are, you'll have to do this column. So 36 divided by 10, we're just writing it down. 16 divided by 10, 49 divided by 10, 36 divided by 10, etc. 4 divided by 10, and 1 divided by 10. So when you add all that up, of course, you get 142 divided by 10, which is 14.2, and that's our chi-squared statistic. That's our stat right there. Now, you see, like in the next example, we're going to have different expecteds depending on our model here, and if you have different expecteds, then of course you're not going to want to sum fractions with different denominators, so you'll not do that. All right, so now what do we do? Well, now you have to know something about the chi-squared statistic. So for this, the chi-squared, it's a sum of squares, and for 1 degree of freedom, we can go back here for a moment before we, just so you know something about the chi-square curve. So first of all, we have to talk about degrees of freedom, because there's a different chi-square curve for each, depending on how many groups you have, how many independent groups you have, okay? So in this case, we can do that part. We have to get the degrees of freedom. Our degrees of freedom are going to be equal to the number of groups, 6, the number of categories. And for all these goodness of fits tests, they're not independent, because once you know any 5 of these, the last difference is determined. Or even here, we know we rolled it 60 times. So if I gave you any of the 5 numbers, to get the last one, you'd subtract that from the sum of those from 60. So you don't have independent groups. So it's the number of categories minus 1. Those are the number that's independent. So in this case, we're going to have 5 degrees of freedom. So now going back and thinking, what you're going to see this chi-square distribution all the time. And it's actually just the sum of independent z-squares. It comes up all the time. So, and here I say, right here, the degrees of, since the last category is determined once you know the others. How many are independent? If they were all independent, if it was a different type of problem and we're not we don't have something, all these categories are really just part of one whole thing. If we just had separate independent categories, then we don't subtract off the 1. It will be the number of categories. Okay, but in this case, it's minus 1. Now, sum of z-squareds. So what would it look like if you just had 1 z-square? The chi-square with 1 degree of freedom, when you have 2 categories, like a 0, 1 box, you only have 1 degree of freedom. Once you know the percent of yeses, you know the percent of nos, right? So it's the same as just adding 1 z-squared curve. So let's think about it. Why would it look the same? Well, let's draw the 2 curves. So we can draw, here, let's draw a z and how, if we squared the z looks like this: 0, 1, 2, and 3, -1, -2, and -3. Now, a chi-square is like the sum of taking z squared. So what happens if I square these negatives? Are they going to ever be negative? No. So the chi-squared's always positive. So we know it's going to be cut off at 0. So what's it going to look like for 1 degree of freedom? This is going to be z squared, which is chi-squared, for 1 degree of freedom. You're just taking 1. So if I got a 0 squared, I'd get let's say, what happens if I get all these negatives? They're going to be the same as these. So let's say I got anything between 0 and 1. 0 and 1, okay? If you square it like a half squared, it's going to be a quarter, right? A quarter squared will be a 16th, etc. So it's going to go way, 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 get bigger and bigger and bigger here. Because when you square a fraction, right, it's going to get smaller and smaller and smaller. So that's what it's going to look like there. See how this is between here and here? It's very probable you'll get in there. So it looks like this. But then what happens if you, and that's the same as, for positives and negatives. What if you get 2 squared? Well, this height here would be where 4 is. So 1, 2, 3, and 4. So that would be here, way out here. 2 would be way out here. So it's going to look like this. That's what it's going to look like for 1 degree of freedom. So this is chi-squared with 1 degree of freedom. And when you have a 0, 1 box, you have 2 categories, and you can use 0, 1, 2 categories. You can do, as we usually do, a z-squared, a z-test. You can use, this is the same thing as you have 2 categories. So your degrees of freedom is going to equal 1. So in this case, we could either do a 1 sample z-test, or a chi-square test with 1 degree of freedom. But you wouldn't be able to tell. There's no direction on chi-square tests. You wouldn't be able to tell. So that's the idea. Now, what does a chi-square test look like with more degrees of freedom? If you have lots of degrees of freedom, the chi-square distribution starts to look a lot like the normal curve. So why don't we check it out right here for 5 degrees of freedom. For 5 degrees of freedom, what is it going to look like, the chi-squared? So why don't we go over here to our all right, so let's just check it out just so you get a feel for what this chi-square curve looks like, because you'll be seeing it a whole lot in all your courses probably. So we'll go to the p-value calculator. Now, as we said before, okay, we can look at this. So we said, here's your z. So let's say we had a z-score of 2. All right, and now we're going to compute the p-value, and we're going to do a two-tailed test, because chi-square can't tell the difference, and that's about 5%. 5%, remember that number, right? It's about 4.55%, and that's the area of both tails. Now, if we do a chi-square test, the z-score, we're going to have to square that, so it'll be our chi-squared will be 4, chi-square 4, and we have 1 degree of freedom, 1 degree of freedom, and our chi-square is 4. And now we're going to compute the p-value, and do you remember we get the same exact thing? So the area of those two tails is now all in the right-hand side. Now what's this left-hand side? We never really look at it. That's like the middle area. Watch. So we do this, left-hand side. That's 95.45. So let's go back to our z. Where's our z? We go back to our normal distribution. And now if we do the middle area with a z-score of 2, and we're going to do the middle area, we should get exactly the same thing we did. Yeah. So that left-hand side on the chi-square is like the middle area. Okay? So that's the idea. So now, what happens with 5 degrees of freedom? I said it's going to start getting more normal. Now, we can't just do a direct translation because we'd have to be adding 5 z-squareds together. So I can't just show you one here. But let's go to the chi-squared. And now, we have, in our example, we have 6 categories, but that's only 5 degrees of freedom. And we got a chi-square statistic of, what did we say, 14.2? So let's put that in, 14.2. And now let's compute not the middle area, but the tails. It's like the two tails. Boy, it's not very likely. We get a p-value of what? 1.439%. Okay? 1.439%. Now, what would be the cutoff to reject the null, like the critical value? That would be when we get what? A cutoff of, remember that 14.4%, excuse me, our p-value is 14, our p-value is 1.4%. Remember that. We'll round to 1. Now, what would be the cutoff for 5%? So we're just going to change this to find out what it would be. Sorry. 5%. And then we'll see what chi-square we need. All right. So this is the critical value, like from here on in is 5%. So we got more than 1107, right? Our chi-square was bigger, our test statistic was bigger than our critical value, so our p-value is less. And at 1%, we would have needed a bigger one. Because we got 1.4%, we would have needed a bigger test. Let's see what that is. That's going to be bigger than our 4.2. So, yep, fine. If we had gotten a value of 15.09 on the chi-square distribution, we would have been on this side, and we would have had p-value less than 1%. We would have had highly significant results. So that's the idea. And look what happens if you have 100 degrees of freedom. It's going to look really like the normal curve. 100 degrees, and you know what? The chi-square is centered at its degrees of freedom. So if we have, it's like the normal centered at 0, the chi-square center is degrees of freedom. So if we do this and we compute that, it's going to be right in the middle. See? A chi-square test with it gets looking more and more normal, and its expected value is right the same as its degrees of freedom. So that's just, we're going to be using it a lot. So I just want you to, chi-square is a great distribution. It's like the normal because you can visualize it. And it's just like the t distribution, and the limit gets close to the z, so you can think of it as normal. We're going to be looking at something called the other distributions, like the f distribution, and that in its limit looks like the chi-squared. So it's kind of nice to know the chi-squared. Let's go back now to our document camera. All right. All right, so now that you know the chi-squared, let's draw that, or no, get a good feel for it, and let's do just what we did. We said that's 14.2, and we're going to draw this chi-square distribution. It has to be positive. It's going to look like here. Now at 5 degrees of freedom, right here, it's not going to look quite normal. It's not going to look like this, like that with 1 degree of freedom, but it's going to look more like still long right-hand tail. Long, long, long. All right, it's kind of like that. And what we saw was that this 14.2, that was our p-value, we got a very small p-value. This area right here, right, that part is what? We got from here on in, we got a probability of what? P-value of p equals 1.44%, but we'll just round it. P equals 1.4%. So what are we going to do? We can say we're going to reject the null at 5%. Why? Because our p-value of 1.4% is less than 5%. So we're going to reject the null. Now, what would we have need? We did do it, so we might as well look at it. I said right here, from here on in, this whole thing was 5%. And that's called the critical value here. The critical value, I'll put a little star, was equal to what? It was 11.07 when you have 5 degrees of freedom. So, since our, just to get you used to this because we'll be doing it a lot, since our chi-square stat equal to, what was it? 14.2 is greater, or further out, is greater than the critical value. The critical value at 5%, we reject the null. It's the same thing. Because if it's further out on the tail, you're going to get a smaller p-value. So that's the same thing as that. Any questions? Okay, so now we couldn't do for this test, we couldn't do a z. What if I asked you, I thought that it was weighted too much towards threes. Look at 3. We had a huge number of 3. We had most threes. Let's say I think it's unfair towards threes. Would I have to do a chi-square test? Could I do a z test? What do you think? How many? What? Yes, why? He said yes, why? Because you can turn it into a 0, 1 box. Exactly, you turn it into a 0 box. If we got this 3, we'd count it as 1, and all these others would count as 0. So we could do, if you can turn it into a 0 box, you could always do a z. And the advantage of a z is you can do your direction. You can say, hey, I think it's weighted towards 3, so you can get half the p-value if you do it that way. If you do a chi-square test, you can't distinguish. It's all positive, so it puts the two tails together. Okay? So with two categories like that, we could do a chi-squared. We would just get whatever we got for the z statistic, square it, that's your chi-squared, and you'll have two tails. Okay? All right, now let's try one where it's not all the same expecteds. So this says a town has 50 Christians, 30 Jewish, and 20 Muslim children. And it says 100 children were chosen to participate in a community project. Of the 100, it turned out 50 were Christian, 40 were Jewish, so 50 matches up with the 50%. That looks like, but 40 were Jewish and 10 were Muslim. So the question is, could it have been a random sample? Let's say they claimed it was random, and people said, well, it doesn't look random. To us, were they favoring one group and not favoring another? So you want to do a significance test for that. So we have 3 categories. So what would our null box look like? Our null is always what? That it was just these differences, that we got more Jews than expected and fewer Muslims, is due to chance. So we have Christian, Jewish, and Muslim. And the null, think about it. What percentage should I put in here? Should I put in our sample percent? Remember, it's always the whole population. So this null is whole population that we're randomly sampled from. So this is what this, and this should go here, 50%, 30%, and 20%. Excuse me, that looks terrible, 20%. All right, and what are we doing? We are going to be taking from here, first I should write the null here. What's the null? That the kids were randomly chosen. Randomly picked. This looks so messy. That goes over there. The kids were randomly picked. And the alternative is, they weren't. Kids not randomly picked. These differences that we see between what we should have gotten, and here's what we observed, 30 and 40, and these big differences were too unlikely to be due to random chance. So how do we set this up? You don't have to do this if you can do it, but in the beginning it might be useful. So let's do it. So let's make a chart, just to keep it straight. So we observed something, And what did we expect? Let's start there. Okay, so what did we observe for these? That's right here. We have 100 total. And we know what we expect, 50, 30, and 20. But what we observed was 50, 40, and 10. Okay, so that's what we've got. And now you know what to do. You just want to see, you take your observed minus your expected. And that's 0, 10, and negative 10, and check that they sum to 0. Now you're going to square those. And you get 0, 100, and 100. Now be careful here. You don't want to total that. Why? Because the statistic that we're interested in is observed minus expected squared divided by the expecteds. And the expecteds are different. So the expected, so you don't want to sum it because expecteds are different, so don't do that. So here it's 0 divided by 50. Here you have 100 divided by, what did we expect? 30. And here we have 100 divided by 20. So we can't just sum those because they're different. Okay? I should write that down. Don't sum. All right, so we've got that. And now we can sum them. It sums to 8 1/3. So that is our chi-squared statistic. Right, that's right, 0. This is equal to 3.33, and that's equal to 5. All right, now what are we going to do? We have to get, first, the degrees of freedom. So the degrees of freedom are going to be what? What are they going to be? 3 categories minus 1. So 2 degrees of freedom. So now let's say you don't have anything handy. You don't have your p-value calculator. All you have, it's an exam, all you have is the table. So how are we going to, let's look at our table. So in the back of the book on page 236, we have the chi-square table. Now, it's going to give you the right-hand tail, which is what we always want. Did something, was it too extreme to have happened by chance? And just, it's a different curve for the different degrees of freedom. So right now we want 5. So we're just getting, so what was our statistic was 8.13. So it's looking like, whoops, we don't have significance. We would have needed, excuse me, I'm not on the 5, I'm on the 3. Sorry. I'm on the 2. You're supposed to correct me. How many categories do we have? Don't let me go on automatic pilot, because then I'd start daydreaming about something else. Okay, so you help me out here. Where should I look here? Say it. 2. We have 2 degrees of freedom, 3 categories. And what was our statistic? 8.33. Okay, look. Here's where you get significance, right here. Anything here, and we're rejecting the null. All right, so 5.99 and bigger, we're rejecting the null. Did we get here? We'd get highly significant, and we got right in between those, between 1 and 5. Does everybody see that? Because we have 8.33. Okay, so it's somewhere between 1 and 5. We don't know, but we got significance at the 5% level. So let's write that down. So p-value is between 1% and 5%. That's all we know from that table. So we'll reject the null. At 5%, at significance level 5%. Okay? All right. And conclude what? What's our conclusion? For rejecting the null, we think the null was that we're rejecting that they were randomly picked, and conclude that we can't say for sure, because we're doing this when we're assuming the null is true, and conclude that there's strong evidence that that's not the right model. They did something else. Our data does not fit the model good. Okay? That's the idea of these significance tests. Doesn't fit this model so well. It's not consistent with the model. And conclude that that's probably not the right model. That there's strong evidence that kids were not randomly chosen. We don't know how they were chosen, but that's probably not the model right there. Excuse me, that's not the model. Were not randomly chosen. I like the name Goodness of Fit because it reminds you that what the null is a model for how things happened. It's your model, and that this is not, your data probably just doesn't fit that. This just isn't it. It wasn't due to chance. It's, there's some other model that, or something. It's just not fitting this one. It's not due to chance that we got these differences. Now, it could be, what's the probability that could be? Between 1 and 5%. So if they really were randomly chosen, between 1 and 5% of the time, we would see these differences. Okay? That's the idea. Now we're going to do our next chi-square test that's very similar. It's using the same exact statistic. Same exact statistic. It's just applied to a slightly different situation. Okay, so let's look at this. So first let's write down our statistic because we're using the same one. See if you can remember it. We're still going to be using chi-squared is equal to the sum over all the categories of your observed minus your expected squared over the expected, and they're always counts. Okay. Now, this is done. It's actually okay. So a chi-square independence test is used to determine whether two variables, each with multiple categories. Before we just had one variable. Now we have two variables, each with multiple categories, are independent. So, a study published in the Journal of Medicine investigated the relationship between tattoos and hepatitis C. And 600, because people thought that when people first started getting hepatitis C, they didn't know what it was caused from. They knew it was because they were having using dirty needles, and so they thought maybe even, and people who weren't drug users were saying, well, wait a minute, maybe it's from tattoos, and they just didn't know what it was from, or maybe from unprotected sex, and so forth. So they did this study at a clinic, a spinal clinic, where the people, completely unrelated to hepatitis C. These weren't people who had any risk factors for hepatitis C or anything. They were just doing some spinal images, and they happened to get all to see if they had tattoos. I mean, because they saw it anyway, because they were, it was what was it for? Spinal stuff. So they had pictures of them. So they looked to see if they had tattoos, and then they saw whether their blood had hepatitis C. They tested their blood for hepatitis C. So it's kind of like a random sample of the population. That's how they thought of it. These are the results. Okay? So the question is, are people more likely, when they have a tattoo, they thought, why do we have three categories? Because they thought, okay, are they getting it from a parlor or from somewhere else, a tattoo parlor or somewhere else? Would they be more at risk from one over the other? And then no tattoo. So we wanted to compare the percentages, or they did in those cases. All right, so these are observed counts, and this is always given to you. This is what you see. So this is given in your data. This is your data. You can't calculate these. You have to have that in your data. Okay, and the null is what? That the chance of getting hepatitis C doesn't have anything to do with tattoos. It's independent. And the alternative is, it depends on tattoos status. All right? So what do you do? So you say if it didn't depend on it, you always figure out the expected, assuming the null to be true. That because if you look at this, 47 out of 626, if you did these as percents, this would be 100%, and 47 out of 626 is 7.5%, and this is 92.5%. So most of the people didn't have hepatitis C, of course. So you'd expect the same distribution everywhere. You'd expect here 7.5% all across here of the people from each. So that's the idea of how you do the test. That's what I say here. Okay? So overall, 47, that's what I said, out of the 626, that's a 7.5. This is how it breaks down. So you'd expect that across the board. Okay, so let's go down here and keep these totals. We know these totals. And so under the null, because we have it, 47 out of 626, we'd expect 7.5% breakdown here. So we'd expect that. That would give us 3.9 here. And if we did 92.5% times the 52, that would be, is that right? No, I did the math wrong here, I think. Hold up. Did I do that right or not? It's not 3.9%, it's 3.9, duh. Okay, here. So out of these 52, this is 7.5%, you'd get 3.9. And here out of the 52, you'd get 92.5%, which is 48.1. So those would add up, etc. Now there's an easier way to do this, because these calculations, a shortcut method would be to do what? Let me show you. So this right here, this 7.5% is just 47 divided by 626. Okay? That's 7.5%. So that's what we're doing. And here, this 92.5% is just the 579 divided by the 626. Okay? And that would be times 52. So the shortcut right here, it says for each cell, multiply its row total, like these are the rows, 47 in this case, times its column total over the overall total. So that's what we did for both of them. Does that make sense? Okay, so it's just easier for me it's easier to remember. So for this one, what would it be? Well, you just take the row, which is 47, times the column, which is 61, and you divide by 626. And you do that for all of them. They're all going to be divided by 626, etc. Okay, so, and we'll get, so for this one, we did this times this, 579. All of these are going to be 579. That's the idea. So you get all those. Okay? Now, obviously, once you get one, they have to sum to 52, so the next one's determined, etc. So when you do this, after you get 4.6, this one has to be 61 minus 4.6, etc. So this one I got here, I'm sorry, there's so many calculations. It's very tedious. So this one would have to be 513 minus that. Very tedious calculations. So these are right here. what are these? There are observed minus the expected. So it's a lot more complicated to figure out the observed. Do you understand why they're the observed minus the expected? Excuse me, they're this the expected. Here, if we take this, your observed, these are your observed minus the expected, sorry, these. So it's a lot of calculations, and it kind of gives me a headache doing them. Do you understand? The idea is simple, but all we're doing is we're going to take each one of these observeds and subtract off the expecteds and then square them. I don't want people to get bummed out by all the calculations. First of all, do you understand what we're doing here? All right, so now we got to do all that. All right, so here we're going to do it. How should we do it? Let's take that first row. Otherwise, I'll get really confused. So let's just take this first row, chi-squared. So what do we have? 17, 8. I'm just going to take these 17, 8, and 22. Those are our observed. 17, I'm going to square them. 8, and then we have 22 squared. They're going to be minus the, okay, so you've got that. We're going to add those up. And the next row is going to be 35 minus our expected squared plus 53 minus the expected squared. And what's our last one? Our last one is this 579. Okay, so we didn't get 17. It's so much more fun to look at what the results were. From the parlor, we didn't get, where did we get more? We'd expect 3.9. We'd expect only 3.9. And look what we got, 17. That doesn't look good for parlors. We'd expect 4.6, and we got 8. For no tattoo, we'd expect 38.5. Is that right? Okay, so that makes sense. We didn't get nearly as many. We'd expect to get a lot more here. We got less. So it looks like it's really dependent, these differences. So let's put our expecteds in. 3.9 for the first row, 4.6, and 38.5. And for the next row, it's 48.1, 56.4, and the last one is 474.5. So that's the deal. And I did this whole thing, and it took me a long time. You're going to make mistakes sometimes, but if you, I tried not to make it too hard on the homework, and you get 58 here. Doing these calculations, I mean, you're going to be doing this using software. I'm not going to, I mean, it's stupid to have to go through all these on your own with these kind of numbers, but I just wanted to give you real data. So I just wanted to show you. So now, when you see this, now we can get to the, is this, you see that number. That's big. Do you know why that's big? Because we'd expect to get, what are our degrees of freedom? How many independent categories do we have? Do you think we can just say 6 minus 1 again? No, we can't. Because look, if you go back here, how many are really independent? Like if I gave you, like, let's say these two of these, what would you be able to figure out from here? If I gave you these two are independent. This one, and this one are not independent, because once you know this one, 3.9, right, we don't even have to calculate that one. Now, these two are independent, so let's say we had those two. Now, or even, are these two independent? Knowing this one is, yep, these two are independent, then this one is determined, right, because this plus that has to equal that. So these two are independent. That one is determined. Could we figure out the whole chart from two independent ones here? That's all I'm saying. Yeah?
Did we divide by our expected frequency when we
No, we didn't. We didn't. I mean, the result is, but we didn't. Good job. This result is, but duh, we didn't. That's amazing. We didn't. What are we going to have to do here? We're going to have to get, of course, we get huge things. We have to divide by the expected. So here it would be 3.9, 4.6. You really are paying attention. So this one would have to be 48.1, and now I can write them more clearly. And this is 56.4, and this is 474.5. I am so glad you said that. Yep. And they're all different. Now, we're not squaring those expecteds at the bottom. So, yeah, if I had added all these up, it wouldn't have helped. I would have had to go back and do all these different denominators. Thank you so much. Very much appreciate it. All right, so now you can see how many independent categories do you think there are here. Want to take a guess? There's not 5. You want to guess? 2, right, 2. So in general, what is it? How do we figure out? You can see why. If you take 2, you can't take these 2 because they're dependent, but any 2 that are independent, like this one and this one, or anything, then you can figure out the other 4 from it. So in general, here is the formula for which just is pretty much just doing what we did intuitively for the degrees of freedom. It's equal to the number of categories for one of the variables. One of the variables had 2 categories minus 1 for, what do I mean by which one you say is the variable is kind of arbitrary. It could either be these 2, and then you're seeing where they got it from, or these 3, and anyway. So this is 2 minus 1 times 3 minus 1, which is equal to 2, and that's where we get that. Now, once you see that, we have our chi-square statistic. Our chi-square stat with how many degrees of freedom? 2 is equal to 58. Now, do you think that's big? Remember I said that the expected value of the chi-square distribution is equal to its degrees of freedom? We're going to look at that more, but you know, it's centered at its degrees of freedom, so it should be about 2 when the null is true. And we got 58. That's going to be very significant. Let's check it out on our computer. Here. So let's go to, here we go. So we'll go to our chi-square distribution, and we only have 2 degrees of freedom, and we got 58 as our chi-square. That's huge. So we're going to compute our p-value. What is it? 2.544 times 10 to the minus 13. So that's putting 13 zeros. That's it doesn't even, chi-square is out of the plotting range. You can't see it. They can't plot it. So because they're keeping these numbers are all, you know, drawn to scale. You know, so they can't fit 58 on here. Like, you know, if you made it twice as long, it would be 36. It's like, it's a little bit off the computer. So we can't even see it. So the probability, what does that tell us? That we would get such a big difference between what we observed and what we expect, just by chance, is pretty much it's just, well, it's tiny. So this isn't just rejecting the null. This is pretty much saying we know it wasn't, that they're dependent. That whether those people had, whether you have hepatitis or not, knowing somebody's status, whether they have a tattoo and where they got it from, helps you know the probability that they have a hep C, for sure. So, but we don't know the difference between, yeah, so that's it. Okay, so the question is, but does it, so let's go back, and this is interesting to think about, because just because you see somebody with a tattoo, are you supposed to get worried? I don't think so, because we don't know if it's causal or not at all. So let's go back to our document camera. and think about this. So now we know, should we reject the null? Yes. The p is so far, p is so small, p is much, 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 much less than 0.1%. So there's overwhelming evidence to reject the null. Overwhelming evidence to reject the null. And what are we going to conclude? That hep C does depend on tattoo status. How do you spell tattoo? This is what, is it with two? I probably spelled it right here. Yeah, 2 T's. Okay. So on tattoo status. All right. So what does that mean? Does that mean, I want you to think about this. Does that mean that tattoos actually cause hep C or not? Do you think so? What can you think of a confounder? So what I'm saying is, here you got a tattoo. What would be a causal link? A causal link would be what? Dirty needles? Yeah, because it would be transmitted through the blood. So this could be somebody before you had hep C and they didn't clean their needles. Or what could be, can you think of a confounder? Something else that's causing hep C and might also be linked or somehow related. I don't know if it was causal, but somehow there's some kind of something that causes related to people getting tattoos. Can you think of what else could cause hep C? It's like, I think unprotected sex and using drugs and so forth. Would that be causing tattoos? Not really causing them, but people who do that, it might be a marker. People who do stuff like that are more likely to get tattoos. At least at this time. I don't think so now. So many people have tattoos. This was well before it was popular. This study was done. And probably now this data is probably not the same. But a confounder might be drug use. So maybe like, people who are just more rebellious in some way, they want to get tattoos, so they do this, and they also get hepatitis C, something like that. All right, so that's the idea. Any questions on that? And now, let's move on. All right, so now I want to show you that, as I said before, chi-squared with 1 degree of freedom is the same thing as a z-test. So here's an example we did before as a 2-sample z, and it has 1 degree of freedom here, and we could do it either way as a chi-square or 1 degree of freedom. So let's just look back and see. This was our falling in love at first sight, which was right here on page 78. We got what? We had this male, we did it as a 2-sample Z, and we got what? A p-value of, in the tails of, if we did a 1-tail test, it was 0.5 or 1. So let's just see if we do it this way as a 2-tail test with 1% p-value, and now let's see if we get the same answer, all right, as we did here. So let's try it. So it's the same data, but with chi-square stuff, so it's falling in love at first sight, independent of whether you're male or female, or does it depend on sex, on whether you're male or female? It's 2-tailed. because you can't specify direction with a chi-squared. And now you have to change the percents to counts to do a chi-squared, to frequencies. So let's do that. Let's say there are 1,000 people. And so here we'll say, what are these? All right. So, and yes and no. So 44% of the men, so that's 44% of these 500 total men. And then I got 220. Now, do you see how there's only 1 degree of freedom from here? I can figure out all the rest, fill in the table. That's what 1 degree of freedom means. If I know these totals here. So how many, well, actually, I don't. I have to get this, 36% of these women, sorry. 36% of the women, so that's 0.36 times the 500, and that is 180. Because, okay, so now I can fill out the rest. So this is 280, because it has to add up to 500, and this is 320. So that's 400 and 600. It's because I didn't know this split here. Okay, so now what are we going to do? So our expected frequencies are what? Our expected frequencies are pretty easy to figure out here because we have 400 yeses and 600 nos. And we have a 50-50 split here. We could do what we said. This would be the row over the column, 500 times 400 over 1,000. But do you see what we're doing? We're saying this is a 50-50 split. So we're just saying half of this 400 is here, and half is here. And the same here. It's going to be 300 and 300. So this is where, excuse me, this is our given percentages. So of course, what I was doing was these are given. So they're clearly not, I can't, any two is not going to give me, any one is not going to give me the rest of the chart. But here is what our expecteds are. So here, like if I gave you any one of these, you could fill out the rest for the expecteds. All right, so what's our chi-square stat? Our chi-square stat is going to be what? It's easier to do because we only have 4 categories here. So we can say for each one of these, we have 220, I'm just going to do the top row, minus 200 squared over 200, plus for this one, it's going to be 280 minus 300 squared over 300. And now the next row will be 180 minus 200 squared over 200, plus 320 minus 300 squared over 300. Okay, so when we add all that up, what do we get? Excuse me. We have to add all this up, and I got 6.67. All right. And now you can do this. These are 20. Each one of these, look at this. Do you see how each one of these differences are 20? So when we square them, we'll get 400 for each one of these. So we get 6.67. 400 over 200 plus 400 over 200. So that's 2 plus 2 plus 400 over 300 and 400, 1.33 and 1.33. Okay, so now what do we have to do? So there's our chi-squared. How many degrees of freedom? The degrees of freedom are going to be equal to 2 minus 1 times 2 minus 1, which is 1. 2 categories here. Don't count the totals. 2 categories, yes and no, and males and females. So we have 1 degree of freedom. So now, since we have 1 degree of freedom, we can compare this. Let's see what we get. to what we got before. So let's go to our PC. And, all right, so we have 1 degree of freedom. And we got remember we got, for two-tailed test before, we got 1% for doing a z-test. So now we should get 1%. What do we get? Well, very close to it, within rounding. So it's very close to 1%. That's the area of the two tails. If you took the square, yep. So that's it. So we got the same thing. So let's go back to our document camera and write that down. All right. So right here, we'll say the p-value. So the p-value is and how do we get that from the calculator? If you want to see what would happen, let's look. 1 degree of freedom, what would we have gotten? Would we get 1%? Let's look. It's probably close to it here. 1 degree of freedom. Oh, yeah. It was just because of the rounding. It's 6.67 is a little bit less than 1%. A little bit less than 1%. We didn't round here. We rounded on our two-sample z-test that had 1%. Okay? So we got 6.67. Remember, we got 0.98%. There it is. Okay? So it's a little bit less. And from the two-sample z-test, we got a p-value of the p-value for two-sample z-test, two-sided, on page 79, wasn't it? 78, on page 78, was approximately 1% as well. That's what I wanted to show you. Okay? So the p-value, I'll write it better here. The p-value for the chi-squared independence test, chi-square independence test, with 1 degree of freedom, I'll put the degrees of freedom down there, is equal to the p-value for the two-sample z-test, two-sided. Okay, and a p-value for the chi-squared goodness of fit test, we might as well write that down too. The p-value for the chi-squared with 1 degree of freedom goodness of fit test is equal to the p-value for the one-sample z-test, two-sided. One sample z, but two-sided. That's what we did before. So those two things are basically z squared is the same as chi squared with 1 degree of freedom. That's the idea. And now, I think this last page is just going over that. But I'm getting tired. How about you guys? Are you tired? Do you want me to finish this up? I could. Guys at home, you can just turn off the computer when you want. That's the advantage, right? Or speed me up. I need some speeding up this morning. I need some coffee. It's not even the morning. All right, might as well fill this in. It's what we just did. I forgot. It was coming up on this page. All right. Specifying a direction to an alternative hypothesis is called a one-tailed test. You know this already. All right. Now, this is what we just said. Which test should we use? That depends on blah, blah, blah. Okay, the love at first sight. That's on page 79. See, we can just do it. I'll show you. And there are, for the two-tail, for both of them, this was like on your exam, for both of them, the null is that the probabilities that men are going to fall in love at first sight is just the same as women. If we do this two-tail, what do we have? We have this alternative that's directional, that's non-directional, two tails. We don't know which way it's going to go. If we have a one-tail, we could say either the one-tail could be for the alternative. We could either say the probability of males is greater than the probability of female. That's what we thought. Or you can also do a one-tail test where it's less. Does not, if you had evidence that way. One or the other. All right? Now, what we got in page 79, we said there was 99% in the middle for both of them. Because we got some z that was, our z for both of them was 2.59. Now, if we squared that, we get the chi-squared. Within rounding, I rounded this a lot. Okay, so now, so where's 2.59? Somewhere here, and somewhere here, somewhere here, and somewhere here. All right, that's between 2.59 and negative 2.59. 2.59, this is all our z, our beautiful z. All right, now, if we do the two-tail test, we get 1% p-value because it's both. So p equals 1%. If we do this one, let's say we did this one, probably, let's say we had males here. So that's the one tail. It's 100. So here our p is 100% minus 99 divided by 2. This is just 100 minus 99. All right, now what's happening with the chi-squared? So now you say the chi-squared is equal to z squared. So within rounding this, we square that, we get something close to that, and now we have the degrees of freedom equals 1, and our p-value should be, the p-value is going to equal 1%. It's going to be equal to that one. Why? Because when we square chi-squared, we're squaring those z's, and if we squared 2.59, it's not exact, but you'll get 6.67. We square that, and then both these tails go on this side. So this right here is equivalent. This is our p equal to 1%. It's equivalent to that one. So you can't, our null here just says that they're different. So the null is always non-directional. I mean the alternative. The null is the same, but the alternative is non-directional. Because it doesn't distinguish, it squares differences. So these two are equivalent. These two are the same. Do you understand that? Okay, that's it. I think that's it. We'll do the next part later. The homework though. Well, we have to, I'm going over. This homework isn't due till Thursday night, and so there might be a few questions you're going to you can probably do them, but you might have to wait till Thursday's lecture, okay? Because we got to get going.